Hello everyone and welcome. My name is Jake Angerman and this is a webinar on MongoDB performance tuning and optimization. I am a solutions architect at MongoDB. A solutions architect is someone who helps customers during the sales process understand MongoDB, understand how to tune it, scale it, and make it performant for an ultimate successful deployment. So a few housekeeping things before we start. This conference or this webinar is being recorded and the slides will be available a day or two after this presentation, so you don't have to take notes. Everything will be available. And also I have some of my team members here to help me out answer some of the questions. So if you have questions during the webinar, you can type them into the chat window and someone will be able to help you. And at the very end, time permitting, I will be able to take some questions as well. So let's go over the agenda. I'm going to define some terms about exactly what I'm talking about with performance tuning and optimization. I'll talk about when to do it. I will talk about some of the tools that you can use to do that within MongoDB. I'll talk about some of the things you can change. And I'll give some examples at the end of some real-world customers who have used these tools and techniques to actually make changes to make their systems more performant. So first I'd like to define my terms. So the title of this webinar is Performance Tuning and Optimization. So what do we mean? What's the difference between performance tuning and optimizing? So I stole a few definitions from Wikipedia. And I'm going to define my terms as optimizing is modifying a system to work more efficiently or use fewer resources. So optimizing is really about efficiency. It's about doing things in an efficient manner, and it's about resource utilization. Performance tuning is modifying a system to handle increased load. So you may have something that's very efficient, but you want to tune your system for performance, so that as your load increases, you're able to handle that increased load. So they're really two sides of the same coin. And if you consider a software development process, when you have the development phase of your software, a QA phase of your software, and then the production rollout, usually you can think of the software process as the development process as this wonderful place with unicorns and rainbows where you have freedom to do a lot of creative things and build new things, and it's very easy to reason about your software, but by the time it gets to production, those are the people who actually have to put it into production and make it work. So I am going to somewhat maybe potentially controversially say that optimization is something that you do during the development phase. It's a proactive process by which you are making careful decisions about how you're designing your software to optimize the way it's going to work in production. And performance tuning is a reactive thing that you do once something has hit production and now you have some sort of limitation or bottleneck and you need to eliminate that bottleneck. So kind of a proactive versus reactive kind of mindset. They're really two sides of the same coin, but I think it's important to define the terms so that people know what I'm talking about in this presentation. So I'd like to talk a little bit about optimization. So there's a famous quote from a computer scientist, Donald Knuth. The quote is, "Premature optimization is the root of all evil." And a lot of people have heard this quote. And in order to really understand this quote, I think you have to take it in context. So Donald Knuth wrote that line in a white paper that he wrote back in 1974 about programming. And if you look at it in context, he was really talking about using go-tos. I mean, that was the purpose of his paper, was to talk about how go-tos weren't such a great thing and that you don't want to start optimizing prematurely because it just turns into this game where you're unrolling loops and trying to write the fewest lines of code, and it becomes this game where you see how tight you can make your code, but it becomes unmaintainable, and no one can understand what you wrote. So the important thing to think about that quote are the three words or phrases that he uses in his paper. So he's saying that premature optimization is about, worrying about the speed of non-critical parts of the program, getting small efficiencies, and doing it prematurely. But I'd like to say that when thinking about optimization, especially in terms of schema design and databases, it is critical to think about optimization as you're writing your code. You do get large efficiencies, and it's not premature at all. It is the right time to do it is as you are developing the software. So I can't take on Donald Knuth. I don't think that would be a fair fight, but the optimization process is very important. You do get big efficiency gains, and it is quite critical in terms of database design. So let's talk about some of the measurement tools. If you're going to measure performance, you're observing some sort of issue in production, and you want to optimize or tune something, you need to have a baseline. You need to have a way of saying, okay, here's how my application is behaving now, and I want to make some tweaks, and then I want to measure it afterwards. So in order to do that, you need tools. So let's talk about some of the areas within MongoDB that you can actually use tools to understand what's going on. So imagine MongoD, the process, is up there at the top of that page. It has various components within it. It's writing things to different places. So some of the things that it's interacting with or parts of it are a log file. So like any software application, it's outputting information to a log file, and you can go look at that log file and see what's going on. You can also use the profiler. That's that middle section. Those documents there represent multiple documents within a collection. So the profiler, as we'll see, writes profile data to a special collection that you can go look at once you turn profiling on. So that gives you the ability to get some sort of historical record of what your application is doing and how the database is performing. And then the last thing over on the right is the query engine. And the query engine is used, you can use various commands to understand how the query engine is performing, understand how your indexes are being used by the query planner and the query optimizer. So we'll look at each one of these components and see how we can use tools to examine what these components are doing or how MongoD is behaving. So let's take a look at an explain plan. So explain is a method that you can run on a query to understand exactly what the query planner is doing. So here is an example of an explain plan that I ran on a collection that's on my laptop. So the format of the command is db.collectionname dot whatever the thing is you're trying to explain dot explain. That's the old syntax that's used in versions of MongoDB prior to 3.0. So you can see here the output of this explain plan. It's at a high level to understand the way this is structured. It's basically a tree structure in JSON, and all the leaf nodes are basically showing you the tasks that they would perform, and then those are kind of rolled up such that the leaf nodes roll up to their parent node, and then you can kind of look at this as a tree. But the key to look at this particular output is I've highlighted it in red. You can see the winning plan. I'm doing a find on every document that has a field called A that's equal to 1. And the stage there is showing me that it's doing a collection scan. So what that means is that the query planner is telling you that it had to actually go into the collection, into the actual data objects, and scan every single one to find the documents that match that query. So another way of saying that is it didn't use an index. So if you are doing an explain plan and you see something that says collection scan, you know that you're not using an index. So that's the old less than 3.0 syntax. In versions prior to 3.0, MongoDB had some fields in the output of explain that were like n and n-scanned objects, and they were very hard to reason about because you basically had to go get a cheat sheet to understand exactly what those things mean. And we'll talk about the differences in the syntax. The new 3.0 syntax is a little bit easier to read. So in this particular example, I did an explain. I found out I wasn't using an index. So now on the first line of this page, I'm saying db.example.ensureIndex on A. And so I've created an index. I run that explain plan again. and now that I find that the winning plan is actually using an index. So you see the stage highlighted there as IX scan, that means index scan. So I have now gone from doing full collection scans to actually using an index. So that's an example of finding something that's not, finding a query that's not using an index and adding an index, and then seeing that the index is used. So that's the old 3.0 syntax, or sorry, the less than 3.0 syntax. So let's talk about the new explain syntax in 3.0. So for those of you who are used to doing explain plans in 2.6, there were some limitations that were a little, caused a little bit of friction. So the nice thing about the new explain plan is that you can now run explain on things that you couldn't explain before. So things like count and distinct, etc. If you tried to run those in versions prior to 3.0, you would get an error because there's no explain method for the count method. So you couldn't say db.collectionname.whatever.count.explain. That would not work. But in MongoDB 3.0, the syntax has changed slightly so that now, that second example, you're going to do db.collectionname.explain, and then that explain method is going to give you basically a view. It's going to give you a collection upon which you can query. So instead of saying, db.collectionname.whatever.explain, you're going to say db.collectionname.explain, and then whatever that query it is that you're trying to do. So there I could actually do an explain plan on the count. So another example are updates. For updating, when you want to run an explain plan in the previous version of the product, an update consists of a query predicate and then the thing that you want to update. So if you want to do an explain plan, you had to break those apart and kind of do the explain on just the query part. Now you don't have to do that. So a corollary of all that is you can now do an explain on a remove without actually removing anything. So that last example there, I can do an explain, and then basically it's going to tell me the explain plan on that remove operation, but it doesn't actually remove anything. So that's kind of nice. That's a nice benefit of the new 3.0 syntax. So when you call the explain method in 3.0, there's the explain method takes as an argument one of three values. So the default value, like if you don't specify anything, like I did in the previous examples, it's basically the query planner, and that says run the query planner, choose the winning plan, but don't actually execute the query. It's just going to tell me like which plan that the query planner was going to choose. So that's good for just understanding, so the example use case is which plan is MongoDB going to run. So the next level of verbosity, if you will, is execution stats. So that will run the query optimizer, which will choose the winning plan just like it did in the previous case, but then it actually runs that to completion. So before, if you had a query that did a lot of work, you didn't want to sit there and wait 20 seconds if you didn't have to. So you could use Query Planner. If you actually wanted to run that query and see how it's performing, you could use execution stats, which would actually go out and run that query. So you have a little bit more flexibility in 3.0. And then the last most verbose option you can choose is all plans execution. So basically it returns information about not just the winning plan, but all of the query plans. So this is when you want to diagnose, say you have multiple indexes and your query might use more than one. This gives you the maximum level of verbosity. So there's now 3 different levels that you can choose from. So going back to my example, here's an example using the 3.0 syntax. So I'm going to do an explain plan. I'm going to do a find. I don't specify anything, so it's going to run Query Planner. It's going to give me the exact same results I gave before. So this is just an example of using the new syntax. So here is an example of using execution stats, which is like the next level up. So I tried to squeeze as much of this JSON document onto a single slide as I could, but this gives you the stuff highlighted in bold will actually show you that it's showing you the execution time in milliseconds. And now instead of N and N objects and N scanned objects and all that confusing terminology, it's actually quite clear. You have N returned, total docs examined, total index keys examined. So it's a lot clearer and easier to use. So I encourage you to use the new syntax in 3.0 for the explain plan. This is great for discovering problems with indexes and queries. Okay, let's move on to the next component we can look at, which is the profiler. So the profiler is basically a 1 megabyte capped collection, and a capped collection is basically a collection that has a fixed size. So when you get to the end of the collection, it kind of wraps back to the beginning and starts writing again. So it's a most recently used kind of thing. So you have a 1 megabyte capped collection, has a special name called system.profile, and there is one created per database per replica set. So what that means is for every replica set, you have a system.profile collection created per database if you turn on profiling. If you have a sharded collection, you'll have to go around and to each particular shard, but for a simple replica set, it's easy to reason about. So basically what the profiler does is it takes every single time you do an operation in MongoDB, it will create one document per operation and create a document that describes the behavior of that particular operation into that system.profile collection. So what you can do is you can go in and query that collection just like you could any other collection. So you could say, show me all the write operations that happened between X and Y time. Show me all of the update operations that took longer than 20 milliseconds, etc. So you can use the aggregation framework. You can use real MongoDB queries on that collection to figure out statistics about how your database is operating. So here's some examples. To turn on profiling, there's 3 levels. So level 1 means log all operations greater than a certain threshold, and the default threshold is 100 milliseconds. So if you want a lower threshold, you could say the second example, 1,20, log all operations greater than 20 milliseconds. So the next level up, let's say you want to log absolutely everything, regardless of its duration. You can set the log level to 2. That's like the most verbose option. And then the 0 turns it off, and the get profiling status allows you to look at the current level. So this is a tool that allows you, so let's say you want to leave it on like running during some period of time, like when you have peak load or something like that. You can basically get a snapshot of how your application is performing and understand how your application is performing by keeping a record of it in the profiler. All right, so we talked about the query engine, we talked about the profiler. There's another area that you can look at, and that is the MongoDB log files. So the log files are structured such that you can see, when something happened, what thread it was, what collection did it happen on, what was the query, how long did it take, etc. So this is very easy to reason about when you're looking at a single line in your log file. So let's say you had a production event and you are going back to see exactly what happened in your log files. It's very easy to reason about by looking at individual lines, but the problem is when you start parsing really big log files, that's hard for a human being to do. These become a little bit unwieldy, and especially when you have sharded clusters with a lot of different moving parts. So wouldn't it be great if there were a tool that allowed you to parse all these files and make sense out of them? And there is. There is a tool called mtools, which was written by an engineer at MongoDB. Basically, it takes your log file, and it's a Python script that parses it and allows you to do various things on that to make sense out of it. So, for example, you could tell there's a component of mtools called mlogfilter, like show me all queries that took more than 1 second between 6 a.m. and 6 p.m. And you could have it analyze your log files, and it would output that to another file that you could examine. So the nice thing about this is it's going to give you statistics like the min, the max, 95th percentile, the mean, etc. So it gives you statistics about all of the queries that it's examining in the log files, and you can rank those and start attacking the problem by the ones that are the most expensive. So this allows you to make sense of a big pile of data and actually get some information out of it. So I highly recommend using mtools. So mlogfilter is one component of it. There's a graphing component. The graphing component is called mplotqueries. So it's also part of mtools. So you can basically say, okay, take my log file, create a histogram of it, and give me a graphical image to represent what's going on. So this is an example of a customer, it was a social networking use case, and the problem they had was somebody really popular created an account and showed up on their social network, and suddenly that person had a lot of followers, and they couldn't figure out what was going on. So this was a tool that allowed them to see, okay, look, we can show that when person X created his account and got a lot of followers, we had this behavior. So that's an example of, in this particular case, it was a schema design issue. So again, mTools is really cool. I highly suggest that you check it out. Real quick, there's some command line tools that you can use as well. IOstat for you Unix folks, it's tried and true. I actually prefer dstat myself. dstat allows you to capture both I/O and CPU information and output it to a CSV file. So it's nice. I like dstat because you can basically take that CSV file and pump it into Excel, excuse me, and not have to write scripts to parse stuff. It does it all for you. So something to check out if you haven't used it before. There are the three at the bottom are included with MongoDB binary. So MongoStat is really giving you the statistics about the read and writes and locks and virtual memory information, kind of like IOstat. MongoTop is looking at read and writes. MongoPerf is a tool that basically allows you to create somewhat of a synthetic benchmark against your disks. So if you want to measure the performance of your disks without any MongoD in the picture, you can use MongoPerf to do that. I don't have enough time in this webinar to go through those, but definitely check them out if you haven't already. Okay, MMS, for those of you who haven't been exposed to it, is the MongoDB management service. It is a management tool, our management suite, that allows you to do automation and monitoring and also backups. And it has alert mechanisms, so you can actually set up monitors of different things and have it send you alerts. So I get a question, I get asked a lot from people like, so what do I look for in MMS? Like what should I be watching? So here's just a quick reference slide. Memory usage is important. You want to see if the memory usage is going up gradually over time or if it's a sudden jump in memory usage. Op counters is important. That's a very good stat. Lock percentage, you don't want your lock percentage to go over a certain threshold. The number of queues, the background flush average, et cetera, et cetera. So again, I don't have time to go into this level of depth for each one of these things, but if you are using MMS, these are some of the areas that you might want to tune into. So now that we've talked about some of the tools, let's talk about actually affecting change. So the process is actually quite simple conceptually. The first is you measure your current performance. So that's important. You have to have the right tools to do that. You have to have some sort of baseline. You have to know what is normal in order to know what is not normal. So you're using a tool, you're measuring your current performance. You take that data, and step two is find the bottleneck. That's the hard part. That's the part where you as a human have to reason about what you're seeing and create a hypothesis, test your hypothesis, etc. So step two is where it all happens. And then three is make some sort of change, remove that bottleneck, measure again, and then repeat as needed. So I think the most important thing is having a baseline. And some of the tools that I talked about allow you to have a baseline of what your expected performance is, what your normal performance is. So let's talk a little bit about what can you change. So you need to change something in performance tuning. What do you change? So there's 5 areas that I've come up with where you can affect change. And actually, these should be done in this order. So the first and most important is schema design. We'll talk a little bit about schema design in a subsequent slide, but that is the area where I would say the majority of schema design is probably the biggest thing in MongoDB to get right, is one of the most important things to get right. The next is the access patterns, like what is the application actually doing? What is its read? What are the number of reads? What is the writes? Are they updates? Are they inserts? Understanding your access patterns and changing the application access patterns is important as well. Indexes, also extremely important. We talked about the explain plan. I'll give you an example of some indexes, some index changes coming up. Tuning the instance itself. I'm not going to go into tuning MongoD itself. We have a page in our documentation called the MongoDB production notes, and I'll talk a little bit more about that later, but that gives you a good framework for tuning your operating system and your I/O subsystem to make MongoD itself performant. And the last is hardware. I put it last specifically because it's the thing that you want to check after you've exhausted the other suspects. A lot of times, a bad schema design or inadequate indexing can appear like it's a hardware problem when it's not really a hardware problem. So you want to eliminate all those other things before you chase down the hardware as a suspect. So let's talk about schema design first. So I'll talk about each one of these. The schema design in MongoDB is the exact opposite of the way you do it in a relational system. So a relational schema, what you usually do is you normalize the data and you write complex queries that do joins on the data. And basically you let the query planner figure it out. The query planner in a relational system is designed to treat all access patterns equally, and you basically just delegate the intelligence to that query planner. MongoDB is very different. MongoDB, you denormalize your data, you create a potentially complex schema, not necessarily, but potentially, and you do it with prior knowledge of your actual query patterns. And that allows you to write very simple queries. And those simple queries, not requiring joins, and they can be very fast. So that is a very different way of thinking about schema design in MongoDB. So let's talk about an example where performance tuning of a schema design resulted in some benefits. So here's an example of an online retailer. They had a product catalog available in I don't know if it was 20 countries, but it was 20 languages. So they had, let's just say it was 20 countries. For those of you who aren't used to MongoDB schema JSON notation, there's a lot of abbreviations and dots in here, but basically the gist of it is underscore ID with the, underscore ID is the immutable primary key in MongoDB. So in this case, the document's key is, primary key is 375. And they had subdocuments for each one of the languages that describe that product. So they had a language like US English, they had one for English, British English, one for Parisian French, one for French Canadian, et cetera, et cetera. So they had a document that contained all the information about that product, and they had the locale translations for every single language that they supported in that document. So what's good about this schema? So it's good because every document contains all the data that you need across all possible locales. So that's really good. It's very efficient to retrieve a document that gives you all the translations that you would ever need. So your application just needs to do one query, and it gets everything that it needs. So the problem with this is that it didn't actually fit the access pattern. So if I'm surfing a website and I want to buy a pair of shoes, and I speak, the U.S. English dialect, I don't need the Parisian French translation. So it is true that you can, so here's an example of doing a find. I want to find ID 375 and just give me back the English language. So this is how the access pattern was actually using this schema, but the data model didn't actually fit that access pattern. So what's wrong with this? So in MongoDB, each document is pulled into memory when it is fetched from disk. So I have pulled in, these entire documents, but I'm only using a subset of what's been pulled in. So in this example, all the data in blue is part of the document, and it's being pulled into RAM, and it's there, but I'm only using it. So I'm essentially using 1/20th of the RAM that I'm using 20 times the RAM that I actually need to. So, basically the consequences was, each document contained 20 times more data than the use case requires, because somebody surfing only needs to know one language. The disk I/O was too high for the relatively modest query load that you would expect from this use case. Now, it is true that MongoDB allows you to use what's called a projection, which says, okay, give me this document, but only project back a subset of it. But even though the application is only getting a subset of that data, still that document had to be loaded into memory, and it had, had to traverse the I/O subsystem to get into memory. So you're using I/O, you're using RAM. So what they did to fix this problem was they created a document per locale. So so you can see in that example down there, the ID is now not just a number, it's a number that has a locale in it. So the application can say, okay, I want product 375 in British English, and it's only getting the name and description for that particular language. So what this allowed them to do, it allowed them to reduce their I/O. So now they had basically 20 times as many products could fit in RAM, and their disk I/O and their latency was reduced. Okay, so that was an example for a schema design change that resulted in performance. So a performance increase. So let's talk about an access pattern. So this is an example customer who had their application behaved in the following way. You could run a query for first and last name. So you want to find all the users of the system, find Bob Jones. So there's a pull down there that allows you to specify exactly, what kind of query do you want to do? Do I want to find exactly equal to Bob Jones? Maybe it contains it, does not contain it, starts with, ends with. So you had a lot of options to choose from in this particular example. So the problem was it wasn't very performant. So here's an example of the log file where it's doing a query for Bob Jones. And you can see in red there that it had to scan 2.6 million documents and only to return 14 of them. And oh, by the way, it took 15 seconds to do that. So this was a system that could not handle this particular query pattern. So what this application was doing, it was basically searching for an unindexed, case-insensitive, unanchored regular expression. So if I'm searching for Bob Jones, I was issuing a query that says, okay, just find any fields that have Bob or Jones in them regardless of where they are. And there was no index on it, and it had to do case-sensitive matching, which was very inefficient, and the regular expression was unanchored. So in other words, for you regular expression people, there was no caret on the left-hand side. So what we did here was we suggested that they change their application behavior somewhat so that instead of searching for a case insensitive with no index, you actually have a separate field of the fields that you're actually going to search for. So in this particular case, you have Bob with a capital B as something that's presented to the user, and then you have a field called FN for first name. That's the thing you're actually going to search for. So then you can create a compound index on last name, first name, and another one on first name, last name, and that allows you to do searches on just last name, and first name, just first name, and vice versa. So now the application, instead of defaulting to contains, which is a very inefficient query, the default search pattern is starts with. So if you don't do anything, you just walk up to the application and type in Bob Jones, it's going to find every Bob Jones, everything that starts with Bob Jones. And that's usually the way people want to use the application. If they want to drill down and do lots of expensive queries, let them select in that pull down something that's more expensive and set their expectations that this could take a while, like it's an advanced search feature. But for just finding like all the Jones, it's actually quite fast. So I set up a test database on my laptop. I took US Census data and I wrote a program that inserted documents that had like random first names and last names. And I can search on my laptop through 13 million names for something like Jones in about 100 milliseconds. So they went from order of magnitude 15 seconds down to right around 100 milliseconds for very, very common queries. So that's an example of changing the access pattern of the application to fit the way MongoDB uses its indexes. All right, let's do another example. So we talked about schema design, we talked about access patterns. Let's talk about indexing. So here is an example of a customer that was having slow queries in the logs. So if you look at the output of the log file there, you can see that they're searching on 2 fields, and they scanned 806,000 documents, and it took 1.1 seconds. So the puzzling thing here is that when you do an index, when you find all the indexes, you see there's an index there. So you're scratching your head like, I don't understand, why is that so non-performant when there's an index there? So if you look closely, there's actually an error in this index. So if you look closely, I'm searching for a subdocument, parent.company. So there's a company field in a subdocument called parent. Likewise for employee ID. So the index was actually created incorrectly. It was created on something that didn't exist. It was created for company and employee ID, and it should have been created for parent.company and parent.employee ID. So this was an example of somebody at some time thought they were doing the right thing by creating an index, but they actually created the wrong index. And once they fixed this, this issue went away. So let's recap the indexing section, talk a little bit about some suggestions for indexing. So the most obvious one, this is going to seem a bit glib, but create indexes that support your queries. Talk to your developers, understand what kind of queries they're doing. You need to create indexes that support the actual access patterns that you're seeing and not something that's predicted. You want to do it for the actual real queries. The next one is create highly selective indexes. This goes for any database. It's not MongoDB specific. We have a documentation page in the MongoDB online documentation that describes how to create a selective index. So I would definitely review that, understand maybe creating an index on a Boolean might not be the best idea. So that goes for any database, not just MongoDB. The next one is don't create unnecessary indexes. Sometimes you can get into this pattern where you are index happy and you're just creating a lot of indexes potentially unnecessarily, and you'll get duplicates. And the problem is every time you create an index, every update or insert potentially could be affected by the fact that you have to now update a lot of indexes. So there are some ways to get around that, and I'll talk about these in the next bullet. But you don't want to just create indexes haphazardly. You want to make a concerted effort to do it right. So you can eliminate duplicate indexes with a compound index. So in this particular example, if I do an ensure index on A and B and C, that allows me to use leftmost prefix. So that single index can handle queries for A and B, and A, B, and C. So you can get some reduced overhead by creating compound indexes where it's possible. The next one is order compound indexes in the following way: equality, sort, and then merge. There's a great blog article that describes exactly why you want to do it that way. I highly recommend it. If you're creating compound indexes, you should definitely read that article. I put the link to it there. It was written by a MongoDB engineer. So definitely check that out and understand the reasoning behind that ordering of the indexes. The next bullet point is create indexes that support covered queries. So a covered query is one in which MongoDB doesn't have to scan any documents. It can just look at the index. So that'll give you some performance, a performance boost. If you have a situation where you are doing a query for fields that are indexed, and the only thing you care about are those indexed fields, then you can use a projection and basically prevent MongoDB from having to look at any documents on disk. It can just look solely at the index to do a very fast query. And assuming your indexes are in RAM, that will be a very performant query. And then the last bullet point is it's a trick you can use in pre-production environments. I stress pre-production. You can basically tell MongoDB not to do any collection scans. The option is called no table scan, but you can think of table and collection as analogous to each other. So basically that's telling MongoDB if you get a query that's going to scan an entire table, like you don't have your indexing set up properly, MongoDB will actually spit out an error and not run that query. So again, I recommend doing this in pre-production environments only. You don't want to do this in production because you don't want your database to go down because you've told it to reject a query. So pre-production environments, it's a trick you can use to catch things that aren't indexed properly. Okay, so the last example I'm going to show is a hardware example. So this is an example from a customer that was reporting, they were doing load testing, they were benchmarking their newly installed system, and they said that they were experiencing a slowdown by a factor of 2 during certain runs of their tests. And they thought it was, potentially something within MongoDB, potentially a storage engine issue or something like that. So I've redacted here the numerical values for the average and max columns just to be righteous and not discuss that openly. It probably doesn't matter, but the numbers don't really matter. What really matters here is MongoDB customer support was able to take the customer's log files and analyze them and create this graph that shows the behavior of their system during the period in question. So you can see between time periods A and B, the inserts basically went to 0. Let's see, the write queue stayed constant, so nothing was being written. What else happened? CPU, the user went down, but IO weight went up. Basically, nothing was being written to the disk. So by analyzing this data, we were able to figure out that because the symptom occurred on both disks, that it was probably something that was common to both disks, like a controller. So in this particular instance, the end result was the controller firmware, like the RAID controller firmware in the box, was actually outdated. And once they updated the RAID controller firmware, things started working again. So again, the customer did everything right in this case. They read our production notes page. They had a RAID 1 SSD for indexes and a RAID 1.0 array for the data, and they did everything they thought correctly. It's just that the firmware was out of date. So I've actually seen issues with RAID controllers where like a battery goes bad on the RAID controller, and suddenly your performance goes down the drain because the RAID controller can no longer buffer things appropriately, so it refuses to cache things the way it used to cache them because it can't be sure that it has a battery backup. So again, this is the kind of thing that you do last in the chain of suspects. You exhaust all the suspects before you get to something as low as the hardware. But this is an example where performance tuning in the hardware made a big difference. Okay, so just in summary, I'm going to give you a list of do's and don'ts. So read the production notes. I talked about that before. If you Google MongoDB production notes, that will give you a list of things that you can tune in the operating system and in the IO subsystem to get a performant MongoDB deployment. I didn't talk too much about instance tuning in this webinar because most of the instance tuning is basically going through that checklist and doing things right based upon the production notes. The next one is eliminate the suspects in the right order. A schema design problem could manifest itself as you might think it's a hardware problem or something like that, but go through this list in this order of schema, indexes, access patterns, the instance, and the hardware, and I think you'll be successful. And then the last and most important for the do's is know what is considered normal behavior. Be able to have logs or records or monitoring data in MMS to understand your baseline behavior. As far as don'ts go, don't confuse symptoms with root causes. That goes with any problem-solving exercise. That's not just a MongoDB thing, but so make sure that you understand the symptom is not necessarily the root cause. And the last thing is don't shard a poorly performing system in an attempt to make it performant. I've had customers say something along those lines, like, we're having some performance problems, and I think if we start sharding, things are going to get better because we can, distribute the load. And I go through this checklist and kind of talk with them about the other performance problems they're having, their symptoms, and it turns out that, sharding would not have helped at all. So if you have a poorly performing system, sharding it is not going to make it more performant. All you're going to be doing is basically replicating a problem across many different shards. So make sure you understand schema design and indexing first, and then start thinking about sharding. But sharding is not a solution to a performance tuning problem. Okay, so we're nearing the end here. I just want to give a quick plug for MongoDB World. MongoDB World is coming up in New York City, June 1st and 2nd. It's a chance for you to hang out with 2,000 like-minded database enthusiasts. We have really good educational tracks, presenters in areas like development, operations, DBA. We have a business track, an ecosystem track. So there's something for everyone there. It's a great place to meet other people who are using MongoDB, learn about some interesting use cases and what people are doing with MongoDB, and it's also a lot of fun. So I have a discount coupon code there for you if you go to mongodbworld.com, and that coupon code will get you 25% off. Okay, so we have about 10 minutes for questions. Let me look through the list of questions here, and at the very end of this presentation, we'll give you a survey. We would appreciate it if you would fill out that survey to understand the effectiveness of this presentation. We can take that feedback and apply it to future presentations to make them more effective. So we really do value your feedback, so I encourage you strongly to fill out the questionnaire at the end. Okay, so let me look at some questions here. Where is that data from for the hardware example? That data came from log files uploaded by the customer. I believe they were IOStat and MongoD log files. So MongoDB support has a tool that can synthesize those files and create that graph. It's one of the value adds of MongoDB support. So that's a great reason to consider production support or an enterprise subscription to MongoDB, because we can help you analyze those problems and solve them. If my collection has embedded documents and we create an index on that field, does it cause any performance issues while inserting documents in that collection or while updating the document in that collection? The answer is no. If you create an index on a field that's in a subdocument, it's treated like any other index. There's nothing special about it. So one of the great things about MongoDB is you can index pretty much anything in that document. So that index is treated like any other index. It doesn't cause a performance issue just by virtue of the fact that you created it. The next question, what tool creates such nice looking reports and graphs? So I touched on that one. Support has a tool, MongoDB support has a tool that will do that. Also the mTools tool that I talked about earlier in the presentation, that is in GitHub. You can go there today and check it out. That mTools tool will allow you to create really awesome graphs. You can change the scale, you can make it logarithmic. So in addition to all of the analyze my queries, command line kind of stuff, you can create graphs with that tool as well. If in my collection I have subdocuments with a small number of elements, can the index improve the performance? Yes, that's similar to the previous question. You can index anything within that subdocument just as if it were a top-level field. There's no restriction there. Is a schema design enforced in the application or in the database? Today in MongoDB, the schema design is not enforced in the application. Sorry, that was an either-or question. It is enforced in the application. It is not enforced in the database. So today it is up to the programmer to come up with a reasonable set of defaults, if you will, and enforce that as a process issue within the software development lifecycle. So today the database will allow you to create documents with different shapes within the same collection. That's totally fine. It doesn't enforce that. In future versions of the product, we are envisioning putting some level of enforcement, but it will be towards the basic end of the spectrum. Things like, there must be this field and it must be an integer or something like that. But it's not going to be, strict, as strict as you might imagine. It will be very, very basic enforcement, but that's coming in the future. In MongoDB, is it possible to lock a table? There is no way within MongoDB natively to do a transaction that crosses a document boundary. There are schema design patterns that you can use to simulate a transaction that spans multiple documents. There's an O'Reilly book that shows you how to do that. But there's nothing within MongoDB itself that will allow you to do that. You have to do that within your application using some schema design. All right, we're nearing the end here. Let's see here. I have 5 million transactions per day. I keep 4 years of data in a relational database. Does MongoDB have some paper about that kind of volume of data? We do have an example on our website. We have multiple examples on our website of keeping that kind of data. Some customers that come to mind. We have a customer, WordNick, that keeps 20 billion documents in their MongoDB instance. Carfax, I believe, has about 11 billion. And there's probably some other ones on the website that I'm forgetting. But if you, I can't remember the URL off the top of my head. But if you go to our website and search for MongoDB scales, you'll see examples of keeping billions of documents in MongoDB. I talked to a customer about a month ago. They were doing 1 billion operations per night on a 3-node replica set on Windows, and they were working just fine. So MongoDB is able to handle that kind of load.
I have put the link to the MongoDB scaling page in the chat.
Thank you, Henrik. Yes, so that link is there now. What's the name of the O'Reilly book that I was mentioning? It's MongoDB Design Patterns, I believe it's called. The person who wrote that book is actually speaking at MongoDB World, just as a plug for MongoDB World again. So it's MongoDB Design Patterns, I believe it's called. All right, so we are nearing the end of our time here. I'm sorry I couldn't get to all of the questions. I tried to get to most of them. Again, fill out the survey at the end. We really appreciate your feedback, and I hope you got a lot out of this presentation. Thank you for your time. I really appreciate it.